Hello students, I am Riekshika Sanwari, Assistant Professor, Department of Physics, Patna Women's College Autonomous. I am here with a lecture on photoelectric effect. As we know that Planck developed the quantum idea, it was extended by Einstein to a new theory of light, that is, light quantum hypothesis. Planck quantized the energy of the oscillator, but as far as the propagation is concerned, his idea was that in space, electromagnetic waves are propagated. According to Einstein, however, light is not only emitted or absorbed in quanta, but it also propagates as quanta. Light thus spreads out from the source as a series of concentrated energy packets or quanta h nu and moves with the speed of light. The individual quantum can transfer the whole of its energy to one single electron without any time lag. The probability of absorbing two or more than two photons at the same time by a metal surface is negligible. These were some of the assumptions of this theory. When photons fall on the metal surface, h nu is absorbed by the electrons or reflected by the laws of optics. In the former case, the incident radiations penetrate several atomic diameters into the metal and electrons at different depths absorb this amount of energy from the incident photon. The energy of the photon h nu is absorbed in two ways. Firstly, emission occurs only when h nu is greater than phi. Phi is the work function which is used to overcome the attractive forces of the positive ions of the metal. Phi depends on the nature of emitting surface. Secondly, the remaining energy h nu minus phi appears as kinetic energy of the photoelectrons. If electrons come from the surface, it does not suffer any collision with another electron. In this situation, it will be emitted from the surface into vacuum with this energy as the maximum kinetic energy, that is represented by equation 1. It is half mv maximum square is equal to h nu minus phi. This is our photoelectric equation. If electrons are ejected from some depth below the surface, they spend some of their acquired energy h nu minus phi in collisions with the atoms. The consequent energy loss is a variable quantity, so that photoelectrons are emitted with a range of kinetic energy ranging from 0 to maximum. When entire energy of the photon is used up in just releasing the electrons from the metal surface and nothing is left for the kinetic energy of the electron, then h nu naught minus phi is equal to 0. That is, phi is equal to h nu naught, which is represented by equation 2. Therefore, we can say that maximum kinetic energy half mv maximum square is equal to h nu minus h nu naught. This is another form of photoelectric equation, and here it is represented by equation 3. A representative diagram of photoelectric effect is shown here in figure 1a. Hence, it is the frequency of the incident photon which is just sufficient to liberate an electron with zero kinetic energy from the emitting metal surface. Hence, the energy of light photon incident on the surface of the metal is not divided, but the whole energy of a photon is used up by the same electron in ejecting from the parent atom and imparting kinetic energy. It is shown in figure 1b. Here, we concisely list the observations of the experiment. The 3 points are mentioned below. Firstly, as can be seen, equation 3 is of the form y is equal to mx plus c, that is the straight line equation. Hence, it can be inferred that the graph of half mv maximum square against nu is a straight line for an emitting surface. For all emitting surfaces, the straight line will have the same slope equal to Planck's constant h. Secondly, when the intensity of incident radiation is increased, the increased number of photons in the incident radiation will cause the emission of more photoelectrons per second. Evidently, the photoelectric current is proportional to the intensity of the incident radiation. The increase in intensity does not affect the maximum kinetic energy. Now, looking at equation 2 and equation 3, we can conclude that when the frequency of incident photon is less than the threshold frequency, that is, for nu smaller than nu naught, no photoelectrons are emitted. For nu equal to nu naught, photoelectrons are just emitted with zero kinetic energy. For nu greater than nu naught, photoelectrons are emitted with kinetic energy ranging from 0 to a maximum value. For nu greater than nu naught, if the intensity of incident light is increased, the number of photoelectrons emitted per second will increase. Now we explain the characteristics of the photoelectric effect from Einstein's equations. The three experimental observations listed in the previous slide follow directly from the Einstein's hypothesis. As we know that the energy quantization was considered in quantum theory of light, photoelectric effect could be understood if the energy of light is not spread out over wavefronts but is concentrated in small packets called photons. Each photon of light frequency nu has the energy h nu, the same as Planck's quantum energy. Firstly, since the electromagnetic wave energy is concentrated in photons and not spread out, so as soon as the photons fall on the metal surface, the electrons absorb the energy h nu and are ejected without any time lag. Hence, there should be no delay in the emission of photoelectron. Secondly, all photons of frequency nu have the same energy. So, changing the intensity of a monochromatic light beam will change the number of photoelectrons but not their energies. Thirdly, if the frequency nu is higher, the photon will possess greater energy h nu accordingly, and so the photoelectrons emitting from the metal surface will have more energy. Next, we say that for nu naught, which is the critical frequency, corresponds to minimum energy phi, which is required for an electron to escape from the particular metal surface, or else electrons would pour out all the time. This energy is called work function of the metal. And we note that electrons do not leave the metal surface of their own as they are bound to the metal. So the greater the work function, the more energy needed for an electron to leave the surface, and if higher is the critical frequency for photoelectric emission to occur. So to pull an electron from a metal surface generally takes about half as much energy as that is needed to pull an electron from the free atom of that metal. With this, we end our lecture. Thank you for watching the video. All the best.